Welcome video 12-3. This is talking about using proportional relationships with an idea called indirect measurement. So indirect measurement, you guys, is figuring out how to measure something that is too big to measure yourself. So like climbing a flagpole is not really all that feasible. So what we're going to do is we're going to use tools like shadows and angle measurements and things like that to figure out how big these measurements that are kind of unwieldy are. And we're going to use similar triangles to do it. Okay, so on the next page, I'm on page 654 here. With explain 1, we're finding an unknown height, and we're trying to find the height of this palm tree over here, which is the height AB. And there are some heights that we know and some shadows that we can see and actually measure along the ground. So what we're going to do here is to set up a proportion between the triangles, because we definitely know that we have congruent triangles, or excuse me, similar triangles, because we've got two right angles here. We're assuming the palm tree is growing straight up, and that when at the same time of day the sun is making the same angle with the ground there. So we've got angle-angle similarity. So our similarity statement that we can make is that triangle XYZ is going to be similar to triangle ABC. So we can set up a proportion. This is wrong, guys. This should actually be a similarity symbol. Change that. So we can set up a proportion that side AB, first two letters there, corresponds to XY. And side BC, which is the shadow that we've measured to be 7.2 meters long, is going to correspond to, BC corresponds to YZ, which is the stick's shadow that we've set up here. And we can see the process that they're walking you through again. If you've got your proportion, remember you can just shortcut right to cross multiply and then get your 1.6 times h equals 7.2, and then when we divide by 1.6 we get 4.5. So the tree itself is 4.5 meters high, and if we think about, remember, a meter is about 3 feet, so we're climbing 14 feet in the air if we want to get to the very top of it, and that's really not all that feasible. So that's why we're using similar triangles to do it. In the next example, we have a flagpole that we're measuring, and so let's fill in the blanks here. The triangles we know are similar. We've got shadows again, so we know we've got right angles, plus we've got these angles with the line of sight to the top with the sun. We're again similar by angle-angle similarity. So we're going to set up a proportion here, and first we're going to look for the flagpole height to be on the top, numerator of the fraction, over the person's height. So we're doing heights of vertical on the left-hand side of the fraction. And then again, we started with the flagpole in the numerator, so we want to do the flagpole shadow over on the right-hand side. And so the right-hand side ratio is the ratio of the horizontal distances, or the shadows. And again, we're going flagpole to person. So substituting what we know from the problem here, we have that the height of the flagpole is our unknown. We have that we know 72 is the height of Sid. He's 6 feet tall, or 72 inches. And then we know that the flagpole's shadow is 128 inches. So again, if we go ahead and cross multiply, we're going to get to 48h equals 128 times 72, and that is 9,216. Dividing by 48, we get 192. So the flagpole is 192 inches tall. If we wanted to convert that to feet, of course, we'd divide by 12, and we would get approximately 16 feet tall is that flagpole. Let's go to the next page for your turn. Make sure you take a pause on the video here we're doing Liam to the height of a tree, and we have his shadow measurements, and we have his height, and we have the tree's shadow, but we do not have the tree's height. So you're going to use similar triangles to set up and find the height of the tree. Moving a little bit down the page, hopefully you finished that your turn there. Don't forget to check the answers posted on our webpage. For Explain 2, now we're finding an unknown distance rather than an unknown height. Sometimes you may not be able to measure distances because there's barriers in your way, or they're just a physical distance that's too far for you to measure. So in this example, we have a very smart hiker who's finding some distances across a canyon by placing some markers. So first she identifies a landmark that she wants to kind of use as a point of reference at X. She's placing a marker directly across the canyon at Y. And then at Y she turns away from X and walks 400 feet in a straight line, and she puts a marker Z there. Then she continues walking straight along the edge of the canyon another 600 feet and puts another marker W there. And then she turns 90 degrees away from the canyon and walks and places a marker when she's able to kind of put the X marker and the Z marker in one single line of sight when they line up. And so she places a marker at V and discovers that that's 327 feet from the edge of the canyon. So the question she wants to ask is how far across the canyon is it? So that's this D right here that we're looking for. So we can certainly see the vertical angles happening in this picture. We've got right angles happening, so we have another angle-angle similarity to set up our proportion with. We're going to do lengths that we know to lengths that we don't know in a proportion. So we're starting with D to 327, or XY to VW, is equal to 400 to 600, or YZ over WZ. And since 400 to 600 does reduce, notice they reduced it to 2/3, that's going to make my life a little bit easier when I cross multiply. So we are simply going to have 3D equals 654 when I cross multiply that 2 times 327 there. And then dividing by 3, we're going to get 218. So don't forget to put in your units at the end of all these indirect measurement problems, because we are using word problems for the most part. So 218 feet is the distance across the canyon that you can find without actually having to stretch a tape measure across and do it. And let's go to the next page. And I'm on page 656 here, you guys. And we're going to fill in some missing pieces for finding a distance across a gorge, similar to what we just did with the canyon on the previous page. So we know we've got vertical angles happening again here at JLK and MLN, and we have right angles being formed with these distances. So we've got another angle-angle triangle similarity. For setting up our proportion, we have JK to NM, and then KL to its corresponding piece, which would be ML, so let's input that. And then the measurements that we have there are D is our unknown, 35 is our NM, KL is 24, and ML from our diagram is 42 meters. So if we fill in what we need here, we've got multiplying both sides by 35, and then reducing that 24 over 42 fraction. That's 4/7, factor of 6 in each one there. And then if I multiply 4 times 35, I get 140. And dividing by 7, I get 20. So the distance across the gorge is actually 20, don't forget your units, meters. Last your turn for this video is number 5 below here. And again, we're going to be finding a distance across a stream with some similar triangles. We'll see you in the next video.